The premise of this presentation is that universal expansion is proceeding at the speed of light. In the early 1900s, while measuring the radial velocity of galaxies, of fast galaxies spinning, American astronomers discovered that light from different distant galaxies was redshifted. Hubble and other scientists measuring the redshift concluded that the universe was expanding, which was a surprise since it was believed that the universe was static. Eventual relativity provided theoretical backing for universal expansion. By the 1950s, the value assigned to this expansion was estimated to be between 50 and 90 kilometers per second per megaparsec, and this became known as the Hubble constant. Is it a constant? Well, maybe a billion light years away, that constant has a different value. Or maybe a billion years ago, that constant had a different value. And as a matter of fact, recent research points toward an accelerated expansion. The problem is, anytime you accelerate something, including the universe, you need a force. A dark force, because we don't know what it is, so we can't find it. While a constant velocity expansion eliminates the need for a dark force or a dark energy. Additionally, it could be that if you have a constant velocity, that's an indication of some event from the Big Bang and whatever followed afterwards. Either way, we need a definite value for the Hubble constant. Now, currently, there are two ways to measure this constant. One, the CMB method, which sets the Hubble constant at around 68 kilometers per second per megaparsec. The second way is a type of variable stars, which set the Hubble constant at 73 kilometers per second per megaparsec. Now, these two numbers are different, 168, 73. And this discrepancy is called the Hubble tension. And astronomers are trying to reconcile the two values. One possible solution to this problem may be to assume that we're living in a volume of space that's less dense than the universe at large. Basically, our local galaxy group is in a void. On the negative side of this, the two values may indicate some kind of flaw in either measurements or maybe there's an unknown variable we're not compensating for. On the positive side, the two values converge toward a narrow value. So for our purpose, let's average the two value at 70 kilometers per second per megaparsec. And let's also assume that the Hubble constant is a constant throughout space and time. So now, to simplify the explanation, I'm going to create an elastic universe, which is about 1 meter of elastic. And I'm going to anchor it to a table here. And 10 centimeters later, I'm going to put a dot. And there's going to be another dot 1 meter away. So I secure the neat elastic to a board, then place the mark 10 centimeters from one end and another mark at the other end. I stretch the elastic to a constant velocity, not that it makes a difference, to a length of 2 meters. When I did that, the first mark moved to 20 centimeters from the origin, and the last mark moved 2 meters. That's how far I stretched it. Since the time to stretch the elastic was the same, the velocity was proportional. So there's a simple ratio formula we can use. Velocity divided by distance, it's equal to velocity divided by distance. It's 1 over time, actually. So if we know the distance and how fast one mark is moving, we can compute the velocity of the second mark. So let's use this ratio to determine how fast the universe is expanding. Again, assuming the expansion proceeds at a constant velocity, I will use my position as the origin and the Hubble constant at 1 megaparsec for me as my first point. So 1 megaparsec is about 3.26 times 10 to the 6 light years. And at that point, the average cosmic expansion should be approximately 70 kilometers per second. The second point, I'll select the edge of the visible universe. And that's 13.8 times 10 to the 9th light years away. Question? What is the universe velocity at that point? Again, velocity divided by distance equal velocity divided by distance. 70 kilometers divided by 3.26 times 10 to the 6 light years. It's equal to velocity divided by how far the edge of the universe is. And if you work out the number, it turns out the velocity that you compute here is 2.97 times 10 to the 8, which is no different from the speed of light, which is 2.98 times 10 to the 8. This tends to indicate that the speed of the universe is expanding at the speed of light, at a constant speed, speed of light. It might also tell you that the speed of light is that particular number because the energy is being carried by universal expansion. Regardless, because of this, the universe edge is invisible to us, and anything beyond it is invisible also. So, looking toward the future, if the universe was actually accelerating, then eventually all galaxies will cross the edge of our visible universe and disappear from view. In other words, the universe to some future human race will look totally black except for the Milky Way itself. But if the expansion is moving at a constant velocity, the galaxy will continue receding from us and they become progressively dimmer. But if you have a sufficiently powerful telescope, you can still see them. They're still visible. Question now becomes, how did this expansion happen? Well, it all began at the Big Bang singularity, which is a momentary event, which was followed by the inflation era, an instantaneous acceleration. During this period, some energy was transformed into what I call pixels of space. The way I look at it is I imagine the Big Bang and the inflation era to be the beginning of the expanding compression wave. This is the Big Bang right here. It's actually, if you can look at it, it's a firecracker. It explodes. That explosion sets off a compression wave, spherical compression wave around it, and the compression wave moves away from the center. So the Big Bang and the inflation era are just a compression. I see them as an expanding compression wave. And at the time, there was no time. Therefore, both events happen instantaneously and simultaneously. That instantaneous expansion, cooled and rarefied the compression wave, the universe. And at some point, the universe underwent a phase transition. And that tied the pixels of space and energy together. And that formed subatomic particles. And that's when matter was created at that instant. That creation of particles removed energy from the expanding universe. It stopped the acceleration and set the universal expansion at the speed of light. It also dropped the density and temperature of the early universe below the creation point of matter. From then on, matter could no longer be created. And afterwards, using leftover energy, universal expansion began creating axions, which are pixels of space and time. That's when time began. So here we have it. At this point, the Big Bang happened, and the expansion went off. So the universe itself is this big thing here. Okay, the visible universe is this section here, and we are at this point here. We're in the center of it. Now, sounds kind of difficult to say we are in the center of it, but it really doesn't make a difference. If we're here, then this circle here, the visible universe, becomes this point here. And if we're standing here, then our universe becomes this piece here. Any way you turn it, no matter where you are, you can just rotate the whole universe and we become the center of the universe. The universe expanding away from us no matter which way you go. So basically, the visible universe is a small sphere, 13.8 billion light years small. It's a small sphere inside the universe itself. Now the question becomes, what if you move faster than light? Well, if you move faster than light, this piece here, the visible universe, shifts along with it. So no matter where you are, no matter how fast you're going, you're just going to be stuck inside the universe itself. And if we go faster than the speed of light, we would actually be able to explore the entire universe, one sphere at a time.